Okay, till now we have been talking about Schrodinger equation and the corresponding Schrodinger theory, but that equation is a non-relativistic equation, okay, and we would like to make a theory which is relativistic. So, I am going to introduce today Klein-Gordon fields. So, I start with Klein-Gordon equation, but before we do so, let us quickly revisit and make some simple remarks about the Schrodinger equation and the corresponding theory. Okay. So, here I have written down the Schrodinger equation. I have put the potential to be 0 here, okay. And we ask one simple question: can we take psi to be real? Do we have a freedom to take psi to be a real field? Okay. Now, note that the operator that you have here, the Schrodinger operator, it is I h bar del over del t, okay, plus h bar square over 2m del square, and this operator acts on psi. Okay, I have put the potential to be 0 here. Okay. Now, if I can take psi to be real, then I should be able to put psi imaginary to be 0. Okay, if I write psi as psi real plus I times psi imaginary, then I should have the freedom to put psi I equal to 0. That is what would mean by saying that I can choose psi to be real. Okay, let us see whether we have that freedom, and you can probably see already that you do not have, because of this factor of I. Okay, the psi real and psi imaginary will get mixed up. Okay, so there will be a mixing between them, and that is why you will not be able to do it. You will not be able to choose psi to be real. Okay, let us see it slightly more explicitly. So, what I am going to do is substitute here psi real plus I times psi imaginary. Okay, that is what I do. And let us operate with this operator on these two components. So, first let us collect the imaginary parts. So, when this derivative acts on psi r, you get I h bar del psi r over del t. Okay, and when this operator here acts on psi I, you get a this iota here, that is what I have collected outside. So, you have here plus h bar square over 2m gradient del square psi I, plus let us collect the real parts. So, when you have this operator acting on psi r, you get a real contribution. Okay. And when the first operator acts on this one, the two i's give a -1 here, then you have an h bar, then you have del psi I over del t equal to 0. Okay. So, that is what you get. Now, if this equation has to be satisfied, okay, the real part and imaginary part must vanish separately, okay, because there is no way a real part can cancel against an imaginary part. See, 2 can cancel against -2, but 2 cannot cancel against 2 times I. Okay, so, these two have to vanish separately, means this should be equal to 0. And that should be equal to 0. So, you get two equations of motion, okay, which are this. Let me write it down: over delta t h bar square over 2m gradient square psi I, this is equal to 0, and the other one is h bar square over 2m gradient del square psi r minus h bar delta psi I over delta t is equal to 0. Okay, so you get these two equations now, and of course they don't look like Schrodinger equation at all, because you have psi r here and psi I here. Okay, so if you say, okay, I can take psi to be real, which means you can put psi I to be 0. Okay, if you do that, then this term goes away. So look at this equation. Okay, this term goes away and it leaves behind only this piece, and this one, when I put psi I to be 0, it leaves behind only h bar square over 2m. Okay, for example, this one does not even have a time derivative involved in this, so this is not even equation of motion. Okay, so you clearly see that psi r does not satisfy Schrodinger equation. Neither of these is a Schrodinger equation. Okay, so clearly psi is truly a complex function. You cannot choose it to be real. Okay, and we will see once we have written down the Klein-Gordon equation, what can be said about the fields which satisfy Klein-Gordon equation. Okay, so this is one point I wanted to make. Let me write it down. So psi can not be taken as real. Okay. Okay. Another point, note that the reason this is not a relativistic equation, the Schrodinger equation, this one, is because you have only one partial derivative of time, right, and two derivatives of space. So del square is del over del x, del 2 over del x square. Now, if you want to have a relativistic theory, your space and time should be on equal footing. Okay, because they mix under Lorentz transformations. So you have to have them appearing equally. Now here you have one single derivative for time, two derivatives of space. So clearly it's not a relativistic theory. Okay, so we should search for a relativistic equation, and that is what brings us to Klein-Gordon equation. And to do that, let's recall how we can write down Schrodinger equation. So the prescription is this: you take energy, okay, and promote it to an operator by the following prescription. So you have energy is del over del t. Okay, then you have momentum, that also you promote to an operator, and this is del over del x. Okay, which is same as these two are identical. And then you say, okay, the particle has to satisfy the dispersion relation, which is E is p square over 2m. Okay, I am looking at free particle. There is no potential, so it's just free particle. Okay, so if you substitute these operators in here, you get I h bar, okay, del over del t is equal to, now you have p square, so you have minus I h bar squared, and you have, let me write, square. Okay, so that's the operator you get, or you can, instead of equal to, you can put a minus sign here and put a, so this is p square and you put a 2m, and you say this is equal to 0. So basically E minus P square over 2m is equal to 0. That's what I am writing in the operator language, which is I h bar del over del t. So you have h bar square over 2m. Okay, then you have minus sign, and then this I square gives another minus sign, so that makes it plus. And that's how you can see that you can arrive at Schrodinger equation. Okay. Now, when you are doing relativistic theory, okay, and you are imagining a free particle, the dispersion relation which is written here, that gets changed. Now, energy relation between energy and momentum is different, and it is E square minus P square is m square. Okay, or you can also write it as P mu is equal to m square, or still you can write it as eta mu nu P nu is equal to m square. Okay, so these are three ways in which I can write the same equation, and eta mu nu I am taking to be plus 1 minus 1 okay, so that's the metric we have. Okay, so I want to do the same thing which I did for the Schrodinger case for this relativistic case. Okay, so what I will do is I will substitute these operators which I have here into this equation and arrive at a similar equation to this one. Okay, but before that, let's have a small remark here. This the same thing, E square minus P square. Okay, this I have put C equal to 1. That thing is written as P mu is equal to m square. So the left hand side, you see both the indices are contracted. Okay, here if you see, for example, the same thing, the mu and nu are contracted with each other, okay, through eta mu nu, meaning there is no free index on the left hand side, which means that the left hand side is a Lorentz scalar. Okay, which means that the right hand side should also be a Lorentz scalar, right, because the two sides should have same transformation properties under Lorentz transformations. So both the sides are Lorentz scalars. So m square is a constant which does not depend on the frame of reference in which you are. Okay, so m square is a constant here, or an invariant, whichever way you say, m square or m. Let's call it m is an invariant. Okay, so this m is called mass, and it doesn't change under Lorentz transformation. This is a fixed quantity. Okay, that's good. Now let's proceed with writing down the equation. So I put I h bar del by del t and square it. So here, so you have two factors of I h bar because I am squaring it, and then you have a second derivative. That's good. I wanted a second derivative. Now p square is again minus I h bar, it gets squared, and you have gradient square. Okay, and this, let me bring minus m square to the left hand side, and this should be equal to 0. Okay, so let's say there is some field phi on which this operator acts and gives you 0. Okay, so that's how you will write down this equation. Now let's put h bar also to be 1. Okay, you can choose units which are called natural units. Okay, and in these units both c and h bar are chosen to be 1. Now once you do that, so you get I square gives you a minus, so you get a minus sign here. This gives again a minus sign, which makes it overall plus, and then you have a minus here. Okay, and then acting on phi equal to 0, and if I multiply the entire equation with the minus sign, with the minus 1, then you get this becomes a plus, this becomes a minus, this becomes a plus, and you get delta 2 over delta t square minus del square plus m square phi zero. Okay, this is our Klein-Gordon equation. Okay, and now we can ask the same question which we asked for the Schrödinger case, Schrödinger equation, Schrödinger field. Can I choose phi to be real? Okay, or as in that case, it is truly complex. Okay, now note that here the operator which you have, the Klein-Gordon operator that you have, is a real operator. There is no factor of I sitting anywhere. Okay, which means if I write phi as phi real plus phi imaginary, phi real plus I times phi imaginary, you will get two equations, one for phi r, one for phi I, and they will be both the same equations. Okay, and these will be Klein-Gordon equations, which means the real part of the field phi will evolve completely independently of phi I. So if you take phi to be complex, you have two copies of the same thing, because phi I and phi real, they satisfy the same equation. And let me write it down. So if you do that substitution, you are going to get this. Was it minus or plus? Plus. Okay, and the same equation for phi imaginary. Okay, so if you take complex, you get two copies of the same thing, because they are not talking to each other, they are not coupled at all, which also means that you can choose to put phi I equal to 0 and take phi to be a real field. Okay, so this is to contrast with the situation in the case of Schrödinger equation. Okay, good. Now what we would like to do is proceed as before, write down an action which will give you Klein-Gordon as an equation of motion when you take delta s equal to 0. Okay, but before that I want to make one small observation again, and let me do that. Yes. So let's return to Schrödinger equation first. Okay, there, if you recall, we just wrote down a few minutes ago. Okay, I'm concerned only with this operator right now. So let's take a state psi, take a wave function psi, which is minus I over h bar et minus p x or p dot x. Okay. Now, when you act with this operator on psi, you will get the energy, right? Because this gets pulled out. So, you get I h bar del psi over del t as E psi. Okay. Okay. And if you substitute the psi in the Schrodinger equation, you will obtain E square minus p square over 2m psi is equal to 0. Okay. Which means that for this to be satisfied, sorry, not E square, E, the energy is p square over 2m. Okay. And because p square is a square of a vector, it will be positive. This is greater than 0. Okay. So, you get energy to be positive here. Now, if you, instead of this psi, you took psi x t, if you start taking this one, let us call it psi prime, to be e to the I over h bar. So, I am taking a complex conjugate of psi. This psi prime is complex conjugate of psi. Okay. E t minus p dot x. Then, if you substitute this in the Schrodinger equation, you will get minus E minus p square over 2m acting on this psi prime equal to 0, which would mean that E is negative. Okay. So, you see that this wave function gives negative energy. Okay. So, we do not work with these kind of wave functions, we work with these kind of wave functions, okay, that you can drop because it is giving you negative energy. Okay. Now, here it was fine. Let us see what happens in the case of Klein-Gordon theory. See, Klein-Gordon theory, we said that we can put phi I to be 0 and we can work with real fields. Okay. So, now a real field you can construct as a sum of a complex field phi and its complex conjugate. So, phi plus phi star is what gives you 2 times phi real, right. So, you see that the same equation, the same wave equation here, or the same function here, this one cannot serve as a solution to the Klein-Gordon theory. You have to also include this one because this is a complex conjugate, and these two together create a real valued field. Okay. So, let us see what happens because of this. So, if you take e to the minus I over h bar E t minus p dot x, okay, and if you substitute it in the Klein-Gordon equation, then you will get the following. You will get E square something strange. Let us go back. Yeah. So, you will get this. Okay. Which would mean that E square is okay. But now you have two solutions possible. Your E is both positive and negative. That is one thing. But you cannot drop the negative energy ones. Okay, this minus choice you cannot drop. You cannot drop because you must include phi star, which is, let's call this phi prime, which is phi star, which is e to the I over h bar et minus p dot x. Okay, and if you write it in this form with the explicit minus I outside, it is basically minus et minus p dot x. So I am assuming that E is positive right now, but then you see that this quantity is the energy of the single of this state in the single particle quantum theory, because when you operate with delta over delta t, it will give you energy minus E. Okay, and you need this solution. You need this solution because you need both the parts. So which means that when you are looking at Klein-Gordon theory, single particle Klein-Gordon theory, okay, treating it as a quantum mechanical system, then you have a issue that you have both positive and negative energy states in your theory. Okay, but this does not bother us at all, because for us Klein-Gordon equation is not a quantum equation. For us it's a classical equation. Okay, we are going to take that as a classical equation, the phi's as classical fields, and we are going to quantize it, and to ask what is the energy of some particular state, which we will have later, you need to calculate the Hamiltonian of that theory and operate on that state, and you can trust that the energy will come out to be positive when we start doing that. Okay, so we will leave the single particle interpretation of these wave function and Klein-Gordon equation and all these things here, and now we move on and repeat the steps which we did few lectures ago, and start constructing the action of this relativistic Klein-Gordon theory. Okay.